In 2019, a breakthrough in quantum computing was achieved with Google's Sycamore processor. Today, the processor is handed over to the Deutsches Museum. We are happy to have you with us.
Welcome to everybody. Good evening in the Hall of Fame of the Deutsches Museum. We are proud to have you here tonight in the Hall of Fame, but also in live stream. I especially welcome our Minister of State for Science and Culture and Art, Bernd Ziebler. Welcome to the Deutsches Museum. I especially welcome, of course, Hartmut Neven, who is kind of the father of Sycamore at Google's AI Quantum Group. I also welcome the president of the Technical University of Munich, Thomas Hoffmann. I'd like to welcome Professor Immanuel Bloch, who is head of MCQST, Munich Center for Quantum Science and Technology. I'd like to welcome Professor Frank Pollmann. He will give us a talk tonight about how can we use quantum computing in solid-state physics, basically. And I'd like to welcome Professor Kranzelmüller. He is head of Leibniz Supercomputing Center here close to Munich in Garching. My name is Wolfgang Heckel. I'm the director of the Deutsches Museum, which has been founded in 1903. And the task is to collect, to exhibit, to discuss the future of science and technology. Of course, we have historical objects, like the first car in the world, like the first Röntgen photograph of the hand with the ring of his wife. We have the first airplane, the Lilienthal-Gleiter. And tonight, I'm excited that we will get a first thing. We would not sit here tonight if we would not have Max Planck in the Hall of Fame of the Deutsches Museum. As everybody knows, he founded quantum theory. And if I can tell you a story, in 1927, when he was head of the curatorium of the Deutsches Museum, he gave a talk in the Ehrensaal here, and his driver brought him with the car to the Deutsches Museum. And the driver said to him, Professor Planck, I have heard your talk so many times already. I could give it. And Max Planck said, well, let's do it. Max Planck took the head of the driver, was sitting in the first row. The driver gave, with the transparencies, talk about quantum physics. Everything was fine. But then a question came. Professor Planck, could you tell me if quantum mechanical states, a two-level system, could have some application whatsoever in the world? The driver here on stage said, oh, my colleague, my dear colleague, such a simple question could be answered by my driver who is sitting here in the first row. Now, tonight, today, we can answer this question because we have here the first of its kind of a processor who did quantum computing. And it was invented by the group of Hartmut Neven in Santa Barbara. And we're very proud that we can get to the museum this first quantum processor in the world. As the first museum, actually, on Earth who receives such an important object, And the object is important because it is probably, hopefully, presumably, a landmark in the history of science and technology, as the objects I have told you before. A landmark because we are entering a time where artificial intelligence, massive computing will be used in so many applications: design of chips, weather forecast, medicine, even art. But we don't know yet what type of problems can be solved with a quantum computer. Well, we have an example, and this is time to ask Mr. Hoffmann on stage. He is representative of Google here in Munich. I should not mix up now where the movies have to be shown. That's why you give me a second. We will have a video, which is a very special video now. It is inside in Google's lab in Santa Barbara. The video from the lab, please let us see.
Hi, my name is Julian Kelly. I am one of the quantum hardware team leads, and we are super excited to talk to you today about our recent results and our vision for the future. I want to start by introducing GQ2. This is our new headquarters of our Santa Barbara quantum campus, and I'm really excited to show you inside, so let's head in.
So this is one of the quantum computer. We actually have one of the Sycamore processor sitting at the bottom of this fridge, which is about 20 milli-K. And you can see this system contains the cryostat itself, as well as room temperature wiring and the electronic on the back. And even for such a system, which we think can only host about, say, 100 to 200 qubits, it's already such a big system. It's much taller than me, and it's big. And in order to, the reason we built such a big system is we have so many stuff to put inside. However, in order to go to 1,000 qubit system or even more, we need to actually think about this system gonna build even bigger and even bigger. Think about the size of this room, and also you think about the facility itself. However, it's also important to think about other part of the stack. So I will introduce to Julian to talk about control electronics.
Thank you, Yu-Chen. I want to tell you a little bit about the control electronics. So the funny thing about the quantum processors that we make is that they sit at the bottom of a dilution refrigerator, but without this, they really don't do anything. They sit around, they're cold, not much is going on. So these control electronics are really what bring the qubits to life. So what they do is they generate analog waveforms that we send into the fridge. They actually manipulate the qubits, and then from the signals that come back out, we can figure out what state the qubits are in. So these custom electronics that we make, we call the aviary system. So it's a creative electronics, and we populate it with birds that all have different functions. So for example, we have heron boards, which have digital to analog converters, eagle boards that do demodulation, and condors that digitize our signals. That being said, if you look at this, you can see that there are a lot of cables here, and this is only hardware for about 50 qubits or so. So you can imagine, as we're looking forward to Milestone 3, getting up to very large systems, brute force is only going to take us so far. So we're really going to have to work on the power, cost, footprint budget of these systems in order to scale to our next milestones. Now, in order to see where these cables actually go, I'm going to send you over to Tony, who's going to look inside the fridge.
All right, thanks, Julian. So here we actually have one of our systems that is currently being built out to house one of our processors. And don't mind it because it's currently under test, so you'll see some additional cables here, but you really get to sneak peek inside. And so as Julian just mentioned, we have hundreds of control lines coming in from the top of the cryostat, and they feed down into the cryostat, which goes through a series of temperature stages, all the way from room temperature down to the millikelvin stage. And we take the control lines and we use these different temperature stages to really extract the heat out of the control lines and also provide additional filtering and attenuation to really provide a clean environment for our qubits and our quantum processor located at the millikelvin stage. Now, what you can see at the bottom are all of these cables, and these will eventually be routed into the processor and through the packaging. And what comes out of the processor is our readout, or the state of our qubit. And that first gets amplified by our quantum limited amplifiers located here, and then through another series of amplifiers that comes out of the system and back into the control electronics that Julian just mentioned.
Markus Hoffmann from Google Munich. You just did a phone call and said, my friends from the Deutsches Museum want to get the first quantum processor of Google to show it to the public. Please bring it over. Was it like that?
I would say it was close to that. Like, we received the request from Deutsches Museum, and I reached out to the team, and everybody was extremely honored to have the opportunity to come to Deutsches Museum and have the Google Sycamore processor next to all these technological milestones, like the first plane, the first computer. So with that, everybody immediately jumped in, and I want to also make a big thank you to the whole team, because like, you can't imagine how many team members contributed to provide material, and then the fab team producing the Sycamore processor. So there was a lot of commitment, and I would say we already had a very good relationship with Deutsches Museum, because think back in 2020, Wieland Hohlfelder made a big effort, the Google Munich lead, to bring the Waymo Firefly to Deutsches Museum. So we had already a very good working relationship and could quickly make that happen.
This is the tradition of firsties who like the Deutsches Museum to disseminate their newest, hottest technology. When will we see a working quantum processor in Munich?
That's a very good question. Like, the Google quantum processor was already used for the Beyond Classical experiment in collaboration with German scientists. So we've been working for the Beyond Classical experiment together with the Jülich Research Center to make the Beyond Classical experiment happen, but also had back at the time Michael Hartmann as a visiting faculty in our group from the FAU in Erlangen. But in addition to that, you ask, when can I now have it? Like, we have now that milestone where we bring the Sycamore processor physically. We will hear later a talk from Professor Frank Pollmann from TUM Munich, who just published a paper together with our group using that processor. So our strategy is we want to accelerate the field and make our processor accessible to the community to go together into the Beyond Classical regime. And with that, we will also in the future have further collaborations with German entities. Like, all our industrial research partners are actually in Germany with VW, Daimler, BASF, Covestro, Boehringer Ingelheim. I could go on, yeah.
It's great, yeah. You already mentioned the talk we will have by Professor Pollmann tonight to explain how he uses already quantum computing in his research. But your words make it easy for me to go over to our State Minister, Bernd Ziebler, which I ask on stage with thank you. Again, please give a hand to Thomas Hoffmann, to Markus Hoffmann. And I would like to start with this just ongoing question, Munich as a hub, as a future hub for quantum computing, science, technology. Bernd, it's your stage.
Wolfgang, Dr. Levin, ladies and gentlemen, well, I'm not the driver, first of all.
He's true, Minister, although he's looking so good and young.
But if there are any difficult questions, there are some members of my staff, and they can give the answer. So don't worry too much. Well, it's really great to have you here in Deutsches Museum, and that links past to present, and of course to the future, and that's the message today. Well, Munich is one of the hottest spots all over the world, the whole Free State of Bavaria. And this Deutsches Museum, it's home of some of the biggest scientific discoveries and, of course, inventions. And it's all a source of inspiration for visitors of all ages. Almost every pupil here in Germany and in Bavaria, of course, visited Deutsches Museum, and they all saw the Faraday cage, and they're all enthusiastic about this experiment with the lightnings there. And even now, when a big part of the museum is being modernized, we can still see most of the exhibits in all this time. And in a normal year, also with the modernization, there is 1 million visitors who are here, and so you can see it's a great place to be here. And of course, there is also the platform Google Arts and Culture, where the things can be seen. So thank you to your company and your business, and of course, there is a YouTube channel. This has been especially popular during the times of lockdown last year. Also, this museum was closed for a very long time, and we're really happy that the museum is open once again, and it has to stay open the next 200 and 500 years, so everybody can see those great exhibits here. It's an outstanding museum, and this museum, it invites us to a journey. We can travel from the beginnings of electronics to the latest developments in the fields of digitization, and thereby to the first revolution in quantum technologies. And it's in this area of Munich great, because you have Garching there, and they're working on almost, well, from outside they look like the same thing, but I think there are great differences I can't even have an idea about. Well, however, by now we have already taken the next steps towards the second generation of quantum technologies, and that's just great, because it's one of the great visions we have to think about the future. And today we are making this important step visible for the public by exhibiting the Sycamore processor here in the Deutsches Museum. And research in quantum technologies has a long history here in Bavaria. I already mentioned TUM, I mentioned Garching, and it's a great area to be. Our universities and research institutions have been contributing to this field for more than a century. They have done groundbreaking research for everything we now call quantum technologies of the first generation. Since the turn of the millennium, computers and smartphones have changed our world more rapidly than ever. Digitization started to have an impact on most areas of our lives. And one company has outperformed for all others. To Google has actually become a verb, even in Germany. As I began 30 years ago, there had been rumors that there should be some more searching machines in the internet, but now there is only one, I think, and it's Google, and to Google is really the verb right now. And we all know the impact of digitization on society, and we all know it will be huge. Thanks to the efforts of Google, quantum computing has made great progress, and the expectations are really high. With the Bavarian Quantum Initiative, we want to play a leading role in the field of quantum technologies. We already talked about it, Dr. Nevin, as we met 20 minutes ago. And the hometown of Deutsches Museum is at the heart of our strategy. With our high-tech agenda plus, we have established the Munich Quantum Valley, and we're creating a unique infrastructure in Germany and in Bavaria. With cooperation between research institutions, universities, and the industry, of course. We need the three of them, and they have to be partners to have the best performance. And further locations for quantum technologies all over Bavaria complement the MQV, the Munich Quantum Valley. Not only Munich, we also talked about Erlangen and the FAU, which is also a very strategic and important partner for us. I'm thinking of, for example, the Cluster Excellence in Würzburg and the newly founded Max Planck Institute for the Science of Light in Erlangen. Max Planck, just look over there, not down, upside. The other one, all over there. And so I can see that some of the involved sciences are presented today, and a warm welcome to all of you. That's just great. 300 million euros we have in the hand to invest it in quantum technologies all over the next 5 years. And that's the strategy behind the Bavarian high-tech agenda. And in the total, we're investing more than 3 billion euros in technologies of the future. And we're really proud that this initiative is seen all over the world. And we want to play a big role in the challenges of the quantum technology. And we want to be an attractive partner for all the scientists all over the world. And we want to have a leading role in AI and super tech. That's the typical small position of the Free State of Bavaria. We all know that there is a huge challenge, but we want to be part in this challenge, and so we're investing in all these things. And thank you, Google is a great partner for these things. For the Free State of Bavaria and also for Munich, thank you for investment in the new Halle in the heart of Munich. That's really great. And Google offers an important job perspective for highly trained university graduates. And I think that's really important to have perspective for the young people, a really attractive perspective. Of course, they're all working for money, they're working for titles, but I think there are some more people who are working for changing and describing and developing the future. There is a mission for the young people, and they want to be part of this mission. And that's something that is really important, and we want to give the frame for this mission the young people they have. Google, of course, is a strong partner for science and research, and various joint research projects speak for themselves. For example, Google's quantum computer. And I'm really proud, Dr. Nevin, to have you here today, because you are one of those great guys who are designing the future. And that's really great, because today's event is a further proof of this successful partnership with you and with you. So Sycamore processor, we can show now the quantum computing is going to make possible, and that's really great. Not only the vision, there are huge steps to have these things done the next years. And I want to thank everybody who has been involved in this outstanding project, and that's really great for us all. Thank you, you're here. You will be with our Prime Minister today, and you will see he's an enthusiastic about designing and framing the future. And so we became those 3 billion euros, and we're working with this money. And of course, there shall be Nobel Prizes, there shall be great honors, but the one thing is the important one. We want to design and describe our future. And that's the mission that gives us the next boot. Thank you so much.
Well, thank you, Bernd. It's quite a privilege and a great pleasure to live in the state of Bavaria, where all these things happen when we whet the appetite of our young visitors in the museum, when they go to the universities later on, become professors, become students, become workers in the modern industries. This is the basis of our wealth in Germany and in Bavaria, of course. So let us give a big hand for Hartmut Neven, who flew in with his family. I might welcome his wife and his son, extra for this event tonight. Hartmut, it's not the first time you're on stage at the Deutsches Museum. Am I right?
Yeah, last time, schönen guten Abend, 2 Jahre her, 3 Jahre her.
Yeah. We have to stay in English because we are streaming for your colleagues in California.
Yeah. But I think guten Abend everybody should understand.
But he's from Aachen, for those who didn't know before. He's from Aachen, and he made a fortune now because he's living in Santa Monica Beach. Malibu Beach, sorry. Malibu Beach. Even better. Hartmut, the stage is yours.
Yeah, herzlichen Dank. Oh, thank you. I should stay in English. So the clicker here works. We should have, yeah, excellent. Goes to show, my wife always says, you build a quantum computer, but then at home you can't change a light bulb. So exactly, I'm a theoretician. Yeah, I just wanted to use a few minutes to recall what Sycamore was about and why it's introduced to the Deutsches Museum today. And of course, the first thing I should do, this is really not my doing, I'm just a messenger. This is the work of a large team And actually, the team is now way larger. It's probably twice the size you see here. But this is the last pre-COVID picture where we were all together. Today, you just get little patchworks. So here's the names of the people who worked hard. Actually, in some ways, it's correct. Historically, this was a team who actually built the chips. That's here under this red veil. And this is how this chip looks. It's a 54-qubit processor. And this was actually not the first quantum processor built. There are others, also using other technologies. But Wolfgang earlier said this is a museum of firsts. So what is first about this? It is the first chip that made good on the promise of quantum computing. It showed for the first time, without any question, that you can do certain tasks using the principles of quantum mechanics that no classical computer will ever be able to do. So that there's an exponential acceleration for certain computational tasks. This nice picture here is, I think it was explained earlier, this is sort of where the chip sits. Now it sits in this I like to think of it sort of as a Zen-like place. It's perfectly quiet, perfectly dark, uninterrupted, and that's where the quantum information can unfold. And when we achieved this result, which at the time we referred to, actually it's not our name, it's a name from John Preskill, the Richard Feynman professor at Caltech, introduced the term quantum supremacy. Today, politically more correct, we call it the achievement of beyond classical computational capabilities. And when we published this in Nature, it made it to the title, and then, because this was a big moment, it made it to the title page of the New York Times, and people used all sorts of metaphors. Oh, this is like the first flight. Actually, I like this metaphor. It's more like a Sputnik moment, because I think it's a more humble metaphor. Sputnik didn't do much. It just circled around the Earth and it beeped. And I feel our processor, this demonstration, was a little bit similar, because the problem we solved was not a problem people have in real life or care for in real life yet. Nevertheless, it was an important mathematical benchmark showing what quantum computers eventually will do. And essentially this demonstration, you can think of it as a computational race. Think of a game show where somebody comes and they write down a mathematical problem, and then you give it to two contestants, the quantum processor and the classical supercomputer, and then somebody's timing. Okay, who comes back with the answer the first? And then at the time, it turned out Sycamore could do this in 200 seconds, while again at the time in 2019, using the best known algorithms then, and the largest or fastest supercomputer then would have taken 10,000 years. So, of course, the field is moving on. Software improves, so if you today would compute it, would not take 10,000 years anymore. But the key point is there is an exponential separation. So even though you make some progress on the classical side, it still takes you exponential cost, which means if you were to repeat this experiment today, let's say with 72 qubits, it would be a similar story again. It would take thousands, maybe by now already more like millions of years to do the task to simulate the task on a classical supercomputer. And the reason for this huge difference is that quantum computers are really a different beast. I always like to say a little bit philosophically, it's the first technology that takes advantage of the fact that we are really living in a multiverse and not just in a single classical universe. But saying it less dramatic, an abacus and a laptop, or an abacus and a supercomputer, classical supercomputer, they're really in the same class. Why? Because let's say if my boy had to do a task at school, let's say multiply two numbers, then you can, we all know, a calculator or a laptop can multiply two numbers, and then there's a certain number of steps you do, which you learn in elementary school. And actually an abacus and a classical computer, they perform exactly this algorithm. They essentially do it in the same number of steps. While for certain tasks, a quantum computer can do the same task, but with much fewer steps, sometimes exponentially fewer steps. And that's why quantum computers are in a different group. And it's important to know quantum computers are so much faster, not because each step is faster. Actually, each step, they're often slower, but because they can do it in so many fewer steps, that's where the huge advantage comes from for certain tasks. And I want to give you, from here, a little bit an outlook. So this was a look back. Why is Sycamore here today? Looking forward, you've already seen from my colleague in the nice video that showed the tour in the lab, where the journey is going. So we want to build a big quantum computer. And a big quantum computer means a quantum for us, or at least that's a goal, is to build a quantum computer with 1 million physical qubits. And that would translate to 1,000 well-protected qubits. And we get there in a series of milestones. So we think of the Sycamore beyond classical demonstration as our first milestone, and then there will be a series of milestones to get to this large error-corrected machine. And I can give you a sense of the next milestone. The next milestone, right now, quantum processors are still a very fragile thing. You know, you have your qubits, and then you come in and you do operations on those qubits. But each operation, remember in the old days when your computer would crash and you had a blue screen of death? So essentially, every time you do an operation, there's a 1 in 1,000 chance that your computer will crash. So obviously, you cannot do too many operations before this whole thing comes down. So you can only run successfully rather small algorithms with rather few operations. And of course, we want to change this and run many more operations. So what we have to do is to do error correction. And the way you do this is like in classical, you distribute the information not that you want to contain in one qubit, you don't keep it in a single qubit, but you distribute it over a group, let's say a 3 by 3, 5 by 5, or 7 by 7 matrix of qubits. And by doing this in a smart way, you can bring, for this whole matrix, the error rate comes way down. And if this matrix is large enough, then the error rates are so small that you can run really long, important algorithms. And then eventually, this is a moniker, this hasn't been built. Once we have the 10 to the 6 physical qubit machine, this is roughly how we think it looks like. And if you wonder this huge fan down there, these are the wires that will go to the qubits to control them and to read them out. And I want to close with, often when you read a press article about quantum computing, they often ask, oh, what are they doing with those machines in the end? Or nobody knows what you can use a quantum computer for. And that's kind of not quite right. One thing that's important to understand is quantum computers will not be good for all computational tasks. They're more like a special purpose coprocessor that will accelerate certain tasks, but not other tasks. So a little bit like graphics coprocessors, which we all know, they're only good at one thing. It's matrix-matrix multiplication. And similar quantum processors are known, well-proven, well-established. Certain important algorithms, they will do exponentially faster. And where this might matter initially the most is in quantum simulation, where you have a system where quantum effects matter, because modeling, simulating quantum effects is one of those tasks that's very expensive for classical machines. They can't really do it, but a quantum processor is well suited for it. So if you want to understand, let's say, certain pharma cores much better and how to design them, you would want to use a quantum processor. And I give you only one example where we could, for example, find big real-world impact. We all know that the current predicament humankind is in is climate change, global warming, and that is maybe one of the directions where we need to pay attention to. And I picked this example because there's another Hartmut here at TNU Munich, Hartmut Ruhl, who is a professor for numerical plasma physics. And he is modeling a reactor type. It's called an inertial confinement fusion reactor. Essentially, you have your fuel in a sort of nano-engineered rods. It's PB11 or boron hydride, and then you hit it with a really strong laser, smash it with a petawatt laser, and then fusion reactions happen, and hopefully enough of them happen that you get more energy out than the laser cost you. And it turns out, I will not go obviously into the details, but to design the fusion reactor well so that you can get a positive energy gain, you have to solve the Schrödinger equation, you have to solve quantum mechanics, and we can possibly help with this. And that would, of course, be one of those examples where quantum simulation could possibly give us the decisive insights to design a nuclear fusion reactor. That would be a marvelous story of showing impact of quantum machines. And with that, I wanted to thank you and hand it to the next speaker.
Thank you.
Thank you.
Thank you very much, Hartmut. Marvel Fusion is the company called, right?
That's the company that does.
Now it's my pleasure to welcome my colleague from Munich Center for Quantum Science and Technology, Professor Frank Pollmann. He's a condensed matter physicist from Technical University, from our university, and he has an interest of fundamentally understanding the properties of matter, also quantum mechanical properties of matters, which are mandatory for understanding, for instance, superconductivity or novel phases of matter. Recently, he started to use quantum computers as a platform to efficiently simulate these systems, such new phases. And together with his team and Google, he has, for the first time, characterized a topologically ordered phase using the Sycamore. And this is what he's going to tell us now.
Yeah, thank you, Wolfgang, for the kind introduction, and thank you all for joining in to this event. I'm really excited to talk about some of the recent results that we obtained using the Sycamore chip. And in our work, we are interested in understanding what's happening if many quantum particles interact. And in fact, and this is what is very interesting, is that if many particles interact, completely new things can emerge. I mean, we are following basically a quote by Anderson saying that more is different. And since I'm going to talk a lot about phases of matter, I want to start with a little bit of an introduction to what phases of matter are. One thing that we are all really familiar with is that water occurs in various phases. So here we see a picture showing the liquid phase and the solid or ice phase of water. If you think about it, that is actually quite surprising that water can show up in phases with such vastly different mechanical properties. So because an individual water molecule is neither solid nor liquid. But if you just put many of them together at sufficiently low temperatures, the water molecules spontaneously form a crystal, and that explains then that the physical properties change. So here, this is an example of more is different. This is an example of a classical phase of matter. However, what we are concerned with are so-called quantum phases of matter. And for this, we want to think about cooling systems down to very low temperatures, such that the physics is determined by quantum mechanical fluctuations. And one prominent example is superconductivity. If you take certain materials and you cool them down, the electrons in the system form so-called Cooper pairs, which then can conduct electricity without dissipation. This, of course, has very important technological implications, as we all know. Another and probably less well-known example are so-called quantum magnets. So there are certain magnets that at low temperatures do not form conventional magnetic order. Right? So magnetic order is something that we're all used to, so we have magnets that stick to the fridge, and this is because they're magnetically ordered. There are other magnets, and I'm going to talk about those in more detail in a moment, that do not order, but instead they form a very exotic state of matter with quite fascinating properties. More about that in a moment. So the question, and this is a question that we ask ourselves in condensed matter as a condensed matter physicist on a daily basis, is why? Why do certain materials become superconducting at low temperatures? Why do others potentially form rather exotic phases? Fortunately, we are in a very good position because we know exactly the elementary building blocks of matter, right? So these are just nuclei and electrons. And for those, I mean, thanks to many people in the audience, like at least the back, we actually know exactly how these elementary building blocks interact. That means, without too much work, we can just write down the equations describing our solids, and they contain all the information we need. This we know already. However, these equations are extremely hard. And as a theoretical physicist, it's easy to write down equations that look scary. In this case, these equations look actually even more scary to an expert because we have to solve these equations for a quantum system. And as Hartmut already pointed out, in quantum mechanical systems, we actually have to consider all possible classical configurations simultaneously. So if we just summarize it, is that if we want to solve these equations on a classical computer that can basically only represent one string of bits at a time, the complexity or the difficulty scales exponentially. It scales exponentially with the system size or with the number of quantum particles we consider. Just to put this into numbers, if we consider the simplest quantum particle that we could think of, this would be just a two-level system, or differently speaking, these would be just qubits. And with the largest classical computer available to us, so that would be the Supercomputers here in Munich, we can simulate only a generic system made out of about 40 or so qubits. And the problem, and the main problem, is now the exponential scaling, meaning that if we just want to simulate one additional qubit, it actually would mean that we have to double the number of supercomputers. And that's going to be quite expensive very, very quickly. To put this in perspective, I mean, the current computer, or the current Sycamore chip has the order of 50 qubits. And if we just put this in comparison to supercomputers, that means in order to go from 40 to 50, we actually have to double the number 10 times, and that ends up in a factor of the order of 1,000. So that fills us with a lot of excitement about the new chips, and this is why I also got excited to try out these chips now for our research. But of course, there are like big open questions regarding the scalability, but there we heard just very exciting news that this can be hopefully scaled up to many, many more qubits in the near future. And this brings me as a theoretical physicist on the agenda, because now we can think about what are efficient quantum algorithms to run our problems on these machines, right? So we have spent, as a community, we spent decades to develop efficient algorithms like DFT, Monte Carlo, etc., that are specialized for classical computers. And now there's an exciting moment that we can think about quantum algorithms. So let me just briefly summarize the statement so far. So the quantum computers, because of their quantum nature, are actually an ideal or like a very powerful platform to simulate the problems that occur when we want to understand quantum materials. So let me now come to our project. So it's going to be a bit more technical now. So we are going to study these exotic phases that can occur in those quantum magnets. And as I pointed out, these systems do not form conventional order like this standard ferromagnet. but instead they form, as I said, some eccentric liquid state. And this liquid state forms what's called topological order. And in the theory world, topological order is has been studied quite a bit and is of big interest. And in fact, the 2016 Nobel Prize was awarded for understanding certain aspects of topological phases. Just to give an intuitive picture, we can actually think about the quantum state being described by what's called a topological invariant. The topological invariant is some mathematical concept that we can illustrate by showing a sphere that can be continuously transformed into a plate. So we can just think of this as being a clay ball, and we can squeeze it until we get a plate. But what we cannot do is to transform it into a torus or a coffee mug. For that, we would have to cut it somehow. So this is now described by a mathematical topological invariant, which is the number of holes. Right? And in a similar way, we can use topological concepts to characterize quantum states. So this is what we are dealing with. That sounds all quite formal, but it turns out that if we have these kind of states, then we know that they have quite unusual or fascinating properties, I would say. And I just want to mention two of them. First, if we have these states of matter, we actually have what's called non-local entanglement. What this means is that the quantum particles that are part of the state can sense each other over arbitrary long distances. Secondly, these kind of states give rise to excitations which are very different from the particles that we are used to. Right? So just if you recall, in our universe, we have bosons. These include, for example, photons or phonons. And we have fermions. These are electrons or neutrons. However, if you have these kind of phases, you can create new types of particles that are so-called anyons. So, and what we did in our work, and this work is currently under review at Science and received really positive feedback so far, is that we first developed a quantum algorithm that generates this kind of state of matter on the chip. Right? So basically we have now code, and once the code finished running, it actually creates a spin liquid state. And once we have this state, we can then analyze it using probes. And one of the hallmarks of these states is that they have this long-range entanglement I just mentioned, and this can be detected by measuring the so-called topological entanglement entropy, which is known from theory predictions. And all I want to show here is that the measurements actually show the expected value of log 2 in this case. And then I mentioned that there are these exotic quasi-particle or these particle excitations that are different from the bosons and fermions that we are used to. And again, on the chip, we actually know exactly how to create these excitations and how to manipulate them. So what we do, and this sounds a little bit strange, but this is what's actually happening on the chip, is that we just think in terms of these particles as being lines in space-time, and now we can braid those lines in space-time and look how this is happening. And for this, again, theoretical predictions exist, and we just exactly reproduce what we theoretically would have expected on the chip. So I do not want to go into further details, but of course I'm happy about private discussions later on. So let me now conclude by saying that I see the quantum computers and the Sycamore chip and its successors as a very good platform, as a very powerful platform to actually simulate and understand quantum matter. And one thing that keeps us busy at the moment, our group and also several other groups in the Munich Quantum Valley at the Munich the MCQST, and namely that we want to develop new algorithms that utilize the power of these quantum computers to understand phenomena in solid-state physics and beyond. And once we have these algorithms, we hope that we can actually predict new quantum phases of matter, and which might be kind of relevant for future quantum technologies. But it's not only about tailored towards new technologies, but there are also many kind of fundamental questions where we hope that these processors will help us to get a better understanding. And these include, for example, how we can derive gravity starting from a quantum mechanical theory, or how we get thermodynamics from a pure quantum mechanical theory. So let me now come to an end, and let me thank also people from my team who did a lot of the work, and this is Leo and Adam. And let me also thank my colleague, Michael Knapp, with whom I did this work together, Christina Knapp, who is at Microsoft Research, and big thanks goes to Kevin and Pedram, who really pushed the experiments on the Sycamore chip. So thank you very much for your attention.
Thank you very much, Frank, for this inspiring talk. If you did not understand everything completely, you will have a chance in the near future to see the first quantum technology exhibit in the Deutsches Museum here. And then you can ask all the questions again you might to ask. When I hear of quantum entanglement, Frank, I always reminded to this cartoon where Bob says to Alice, you are the one for me. But Alice, having in mind the quantum physics lectures, Feynman, whatever, she answers, but Bob, how can we be sure in a quantum world, right? But entanglement is, and quantum cryptography is hot topics. Thank you very much for giving your talk. Now we come to the fact that this processor still belongs in the moment to Google. But Hartmut brought it yesterday morning with him in his suitcase. No, he told me actually this today that it was a necklace of his wife and he just stole it. No, also not true. To see the real story behind, we got the package some weeks ago, and our curator, Luise Allendorf-Höfer, who is responsible for the Future Electronics exhibition at the Deutsches Museum, she unboxed it. And this is why we get a little movie now, Unboxing the Secret.
Recht herzlich willkommen hier im Deutschen Museum im heute etwas windigen Innenhof. Mein Name ist Luise Allendorf-Höfer. Ich bin Kuratorin für Elektronik und Nachrichtentechnik hier im Deutschen Museum und ich freue mich, Sie an dem ganz besonderen Moment für uns teilhaben zu lassen. Heute wird nämlich ein außergewöhnliches Exponat in unsere Sammlung aufgenommen. Dank der fantastischen Zusammenarbeit mit Google wurde uns der Sycamore Quantenprozessor gestiftet, um ihn jetzt als ersten seiner Art der breiten Öffentlichkeit zugänglich zu machen. Mit dem Sycamore gelang Google im Oktober 2019 dieses bahnbrechende Beyond Classical Experiment, in dem der Sycamore innerhalb von 200 Sekunden eine Berechnung durchführte, wofür klassische Supercomputer 10.000 Jahre benötigen würden. Und dieses bedeutsame Exponat findet jetzt hier im Deutschen Museum seinen einzigartigen Bestimmungsort. Ich freue mich, wenn Sie mit mir eintauchen in den Bereich des Museums, wo unsere Spezialisten den Sycamore quasi für die Ewigkeit vorbereiten. Wir begeben uns nun dazu in unsere Objektannahme. Wir sind hier nun in der Objektannahme und mit mir ist meine Kollegin Susanne Griesbach. Sie ist Restauratorin und Spezialistin und nimmt unsere Objekte in Obhut. Und nun bin ich ganz gespannt, wie sie mit dem Sycamore umgeht. Ja, gerne. Schauen wir mal nach.
Dreimal eingeschweißt.
Dreimal eingeschweißt. Gut. Wir tragen nun Masken, weil wir ihm uns so stark nähern, denn er ist äußerst empfindlich gegen Staubeintrag. Aber wir möchten ihn ja betrachten, denn die Faszination des Originals, die zu erleben, dafür sind wir hier im Deutschen Museum. Susanne, wie geht es eigentlich jetzt weiter mit der Objektannahme?
Nun werden wir den Chip in die Datenbank aufnehmen und dafür gehen wir an einen anderen Platz.
Wir sind hier an der Fotostation, die zu Dokumentationszwecken unserer Objekte dient. Und Susanne, kannst du uns erklären, worauf es ganz genau eigentlich hier ankommt?
Ja, also hier fotografieren wir all unsere Exponate. Wir fotografieren mit einem Grauabgleich und mit einem Maßstab, sodass man sofort eigentlich auf den ersten Blick sieht, wie groß ungefähr das Exponat ist.
Ja, Susanne, liebe Kollegen, ja, vielen Dank dann für diesen Einblick in die Aufnahme des Objekts ins Deutsche Museum. Und ich hoffe auch, unseren Zuschauern hat dieser Einblick gefallen. Jetzt wird der Sycamore Quantenprozessor für seine nächste Etappe vorbereitet, denn er wird ja öffentlich gezeigt werden in einer Vitrine. Und dazu freuen wir uns auf Ihren Besuch. Vielen Dank.
Yeah, thank you to the team of the Deutsches Museum. Now it's time for Christmas. Opening the present, I may ask on stage Bernd Siebler, Hartmut Nehmen, Markus Hoffmann, and Luise Allendorf-Höfer, if she's here. Yes, she is. And now we may tear somewhere, no? Here it is. You may clap your hands now. Thanks again, Google. We're expecting much more to come in the future.
Thank you, Deutsches Museum, for the honor to have this artifact here.
Thank you so much. It's really great to have it here right now.
Cooperation is
The place to be.
the place to be. Yeah, cooperation is what whets our appetite for the future. And it's my pleasure to tell you that from tomorrow on, you can see this, everybody can see the Sycamore in the historical area of the Deutsches Museum just now on this side. And from next year on, in the new exhibit, Electronics, of the newly renovated Deutsches Museum in 22. Thank you so much, and I may invite you for a small glass of champagne or
Whatever.
Prosecco or water.
What about Bavarian beer?
Beer also possible. Alcohol-free, with alcohol. We both are from an area in Bavaria where we certainly like...
We don't drink alcohol-free beer.
No, never. Thank you very much for being with us. Thank you for everybody who followed in the stream. Thank you again to the Google team. So many people are behind this event. Thank you for the team of the producers here, for the team of the Deutsches Museum. And come again to the Deutsches Museum and become part of the journey into the future. Thank you so much.
Right above you, night breezes seem to whisper, I love you. Birds singing in the sycamore tree, dream a little dream of me.
This is why the name